welcome to the course on FPGA based signal processing systems. Today we'll be looking at the Verilog modules to develop for the FIR filters, what we had learned. So the FIR filters, the design which we had learned was using the window method, different window functions, and then what is the relation between these samples of the main lobe width or the side lobe width of the window, and the relation between the filter design. So how the impulse coefficient should be, and what is the impulse response of the FIR filter, and so on. So when we try to develop that model, the structure what we had learned, linear phase FIR filters, as well as the case of direct form structures also. So in this filter structure, how we are going to code that in Verilog, and what is the things which need to actually look into when we get the response of the filter. So FIR filter will be dealt in this lecture. So before getting into this, we need to know that because the coefficients needs to be stored, or it needs to be specified to the Verilog module. So how are we going to specify the coefficient? Okay, the shift operators can be used. So how the shift operators will be helpful in making the coefficients, okay, in the module. So the shift operators we had already seen in the very beginning of these lectures. Suppose it is 0 1 1 0, the 4-bit number, which is the left shift by 1. This is going to be the 6, this number 6, shift left, which results in 12. So we get 1 1 0 0 if you shift left by 1 bit, and no problem here. And if you have 6, same, right shift by 1, then this would result in 3. So this can be used for multiplying a coefficient or dividing the coefficient by 2. So 6 will be multiplied by 2 if you left shift it, and if you right shift it, it will be divided by 2. So there is no problem. So the left shift operator and right shift operators are known to us. Now the thing is, if you see 6, there is a 3 less than symbols here. The less than operators. These less than operators, what is the difference between this left shift and this left shift? This is the 3 more than 2, it gives the arithmetic shift. Okay, so this is called the arithmetic shift. This is just simply the shift. So left shift, and this is arithmetic left shift. In that case, the 6 would result in again 12. There is no difference between this and this when the number is even the signed or unsigned. So arithmetic shift doesn't make any of the difference in the left shift. Whereas if you take 6 and greater than 1, arithmetic right shift, the 6, so also gives you the 0 0 1 1, which is 3. So it seems that what is the difference between this arithmetic shift of the left shift and right shift, arithmetic left and arithmetic right? So it results the same when the number is unsigned, that is the positive number. So if you look at the same thing if there's for the signed numbers, okay, so suppose this is the -4, okay, so 4 and the sign magnitude 1 is given. If it is less than 1, if you left shift it, yes, this is going to give 1 0 0 0. The resultant would be 1 0 0 -8. So it's a signed decimal, it is -8 here. So same right shift by 1, that -4, the number right shift by 1 gives you this 6. Okay, so but you need to be right shifting, you are expecting that to be the division. So that's fine. Here at the left side, left shift and right shift operations for the sign number, and just it is skipping 1 at the right. So the 1 1 0, the last bit is with 0. When we have the arithmetic shift for the same number, so it is again result in, if you just remove it, that this will be left shift 1 0 0 0. So this is going to be -8. So this and this doesn't make any difference in the case of sign number as well. So when we have sign number right shift, that is arithmetic, then we need to be really see this would result in, if you shift it 1 1 0. So this 3 bits would come. What would be the last MSB will be filled with? This will give you a signed extension in the case of arithmetic shift, arithmetic right shift especially. So when left shift, there is no, I mean, you are not, when the LSB will not be filled with one or so this thing, whereas in the case of right shift, yes, this arithmetic shift makes a difference, which is the sign extension of the number will, this is extended one bit will be extended, so which is resulting in -2. So instead of going for a right shift simply, so you can have this number -4 divided by 2, which is arithmetic right shift. The MSB sign is extended, so that's the difference. So we'll be using this arithmetic shifts in the FAR coefficient usage, actually in the Verilog module. So the module which is generated to show you the same example over the Verilog module, the arithmetic shifts, ridge number A, B, C, D, there are four numbers and then outputs of 4 bit. So just assign the number 1100, that is the minus 4 bit 1100, just to see the result, and wait for 100 nanoseconds and then end. Initial Y is left shift and then YA, YB is right shift, B same number is given everywhere, and the C is arithmetic left shift, D is arithmetic right shift. So this function, this module, how does it give the response here? So you can see A, B, C, D are the same values which are the inputs plotted, and -8 left shift and right shift, and you can see the left shift, there is no difference between this two, -8 and -8 in the waveform editor, whereas here that makes a difference, this two will be different. So this is the case not equal, so -2. So it is apt to use the arithmetic right shift in the place of dividing this number. This is about the Verilog shift operators. Now we are going to use this shift operators in the coefficient and using the taps of the FIR filter. So taking the module and module FIR, this is the developed module or the FIR design what we had done. So we will code this assuming that this has a 4 taps filter, FIR filter. So input clock which is necessary, and reset signed 8-bit input, and output signed Y. So the input and the output X and Y, clock and reset. Now this is the system clock, asynchronous reset. We are going to, when you want to stop this operation of the filter, just you can stop at any point of time, so using the asynchronous reset, and then system input and system output are there. So now declare these taps, that is 4 taps in the sense 4 coefficients we have. So 4 coefficients of the filter, 0 to 3, you can see the 2-dimensional declaration of the tap, which is for 0 to 3 4 coefficients, and 0 to 7 8 bits wide each. Signed, and integer is a loop I which is varying for the increment of the operation. So after this, always at passage of the clock or passage of the reset, this is asynchronous reset. Begin. So begin this operation with the computing output Y with filter coefficient weight. So in the filter structure, if you see that x of n is input, and then the first in the structure you have the first coefficient, and then it is delayed, and then next coefficient, and then it is delayed, and like this, and then these are added. Okay, so we can have single adder or the multiple adder, or each will be added. This is Y of n. So to compute this thing, actually, what is the compute Y? Okay, so the coefficients here are given as -1, 3.75, 3.75, -1. It's of course a symmetrical one. Now, getting the if in the always block, first statement should be reset. If reset, begin. What should be that? For I is equal to 0, I less than or equal to 3, I equal to I plus 1. The increment is 1. Tap I equal to 0, that is less than or equal to, here is the non-blocking statement. First assign this, if there is a reset to true, then all the taps needs to be 0. So tap all of them 0, that is H of 0, H of 1, and H of 2, H of 3. Okay, 0, 1, 2, 3. So, this is tap 0 0 and y output also 0 in that case. So, end if reset is not true, this what should be, then else begin. So, we would be giving the y output, else what should be the output. If reset is 0 or reset is reset goes into this here, reset 1, output is essentially 0. If not, then what should be the y? Okay, so the y equal to, we have this coefficients that is less than or equal to minus tap 0. Okay, so this tap 0 is minus whatever the value here in the tap 0. Okay, so that tap, actually we are making this tap 0 1 2 3 8 bits wide, and the four of these coefficients, and the input is actually fit to the taps. Here the input, it's given to the tap and then delayed for the next operation. So, tap 0, it is minus 1 here, and then tap 1, which is here 3.75. So, you can see this left shift, arithmetic left shift, tap 1 and plus tap 1 plus tap 1 right shift arithmetic, and then arithmetic right shift 2. So, this essentially represents minus 1, okay, and the value what we have in the tap. Supposing it is here, you can see. So, this is supposed to be 1, and before if you give the input whatever, this 1 into x, whatever the input, we would take it. So, 1, and if you left shift it, that would give you 2, that is multiplication as we have seen, and right shift by 1 right shifting by 1, that gives you 0.5, and then again right shifting this by 2, that is tap 1 by 2 will 0.5 by again 2, that is 0.25. So, adding up together it gives you 3.75 the coefficient. So, this is one way of making the coefficient, if the coefficient can be rounded off with the shift operator. Okay. Similarly, for tap 2, the same, because this is also 3.75, tap 2, this gives 1, and left shift by 1, and then right shift 0.5 if it is one right shift. If it is another right shift, this is going to be 0.25. So, add up together 3.75 to the tap 2 as well. And the tap 3 is minus 1 again. So, this is why less than or equal to is this. So, that will be a tap out of the value we stored here in S in tap 0 1 2 3. For I equal to 3, I less than 0, I equal to I minus 1. Let us see, each tap it is shifting, that delay was there, tap I minus 1 is shifted to I every clock cycle here. So, this is shift 1. So, starting from 3, and then 3 minus 1 2, and then 2 minus 1 1, and 1 minus 1 0. So, 3 2 1 0, all the will be 1 by 1 shifted. This is a shift operation that is delayed or used. So, x is fed to tap 0, you can see that is x, the input which is given to tap 0 and which would be here, and then this x will be keep moving in the next cycle and next cycle, so on. So, this is end. So, in the end module. So, we have this additions we have taken care of here, the additions, the whole addition of the filter structure y, computing y is taken care here, and multiplication also taken care with the tap only. Okay. So, and movement of one to another is through the for loop. So, here this is end module, and then we go to the test bench FIRDF1. So, clock reset, and x input is 8 bit, output y is again 8 bit, instantiate that module, and then initialize the input, clock 0, reset is 1, x is 0, and wait for some time, and then add stimulus over here, x is 10. So, here what we give is reset makes 0, we make the 0, and x is 10, x is 10 for some time, and then making it x equal to 0. This is to find the impulse response of the for some time of the 10. Okay, what would be the response end? So, let us see the response always at first. Anyway, clock is required, hash 50 as we do in all other codes, clock is equal to not clock, and display this content x and y, input and output with respect to the time, monitor, $display and $monitor. So, from this is the test bench which is showing the output here. You could see this 0, the x input is 0, and then made 10, after that it is 0. So this for one cycle from here to here, this is the place where reset is made 1 and then reset is 0. So when reset is 1, that output will be 0. Okay, after this is 0, still this input feeds through and take the output. These are the outputs which you get every clock cycle for the input which is given. Input is stopped after that. This is an impulse response of the filter, which we can see in the another radix. So decimal 0 and then 10, reset is 1, the waveform editor which gives this 246, 37, 246, 0 and so on. So this is the impulse response of this filter. Okay. You can see for the coefficient, the input is 10. Okay. So this is the case of the 4 coefficients. Okay. So we can also have the another example which is for the transposed structure. So the transposed structure is where the delay and the coefficient, the delay places get exchanged, if you remember that, x of n and then coefficient and then delay it and then add x multiply with another coefficient and add them and then delay it and so on. So the filter, how this filter is going to be designed for the transpose structure module, and the module name clock reset, load x, x in, c in and y out. So output, input and load x is the operation where coefficients are loaded and c in is the first coefficient, how we will be loading it. Okay, so there are some bits specified because of the length of the input and other things. So input bit width is W1, which is 9 using the parameter, and this is also multiplier bit because coefficient and the input should be multiplied here. So this is 18 bit wide. Okay, input is also input, you have this 9 bit and then W2 2 into W1, at least an 18 bits required in the multiplied output, and adder, which is one bit extra from the multiplied output, and the delayed input will be added W3, and W4 is the output bit width. So from this, let's take this filter length as L equal to 4, and then input clock, that is a system clock, and input reset. After this, the load x, load the x is whether load the coefficient or shift operation should be done for adding the getting the response, adding and getting the response. So input sign x in the input 0 W1 minus 1, that is going to be 9 bits here, the input, and then coefficient also will be 9 bits, coefficient data input 9 bits, and then y out is 11 bits out of this after adding everything. Now we get the adder array of 4 coefficients, 4 depth are A0, A1, A2, A3. So this is from 0 to 3 is of 0, A1, A2, A3, and then width is 0 to W3, that is 19 bits wide, 4 adder arrays. These are declarations: input, x in, c in, y out, and the A adder array we have declared. So this the declaration you can see, and always at passage of the clock, if reset, this is also asynchronous reset here. Begin block has the name, you can see load, you can, this is optional, you can give integer k. For this, if reset is true, then begin asynchronous clear here for k equal to k l minus 1, or the length of the filter, k to k plus 1, ck, all coefficient make it 0, that is x is also 0. Clear them, this initialize this arrays to 0, and then else if load x is not load x, it is not 1, then what should be load the this is load the coefficients, that is c in the first coefficient to c3, and then c3 to c2, c2 to c1, and then similarly here, and then last coefficient c1 to c0. So this is the case of loading the coefficients in that array of C, which has and then else after loading. So if give the x into x. So one sample at a time of xn. So xn will be data samples, so which we need to take at least one by one here and load it to x. Xn is the input which is given to x, structure end, and then compute the products always at passage of the clock or passage of the reset. Now, so that this is this always block, the previous always block having the initialization and storing coefficients. Here you see, here always at passage of the clock, passage of the reset, if this is for reset, and then initializing the coefficient, and then have the coefficients stored in it in arrays. This is storage. After this, assign this input x to xn and then end. This is ending over here, the first always block. Next one, compute this for always passage of the clock, passage of the reset. Otherwise, here the transposed filter additions we can compute here, integer k. If reset, again for k values, array adder value, all of them make it 0, else begin what should be done here. So a of adder 0 is the sum of the product P0 and A1. So we A1 less than or equal to P1 plus A2 and A3 and so on, P3. So how do we get this? And this is the adder operation. So after delay, x multiplied by the coefficient and then delay it, and x multiplied by another coefficient, add it, those two will be added, and then delay, and then x is again multiplied with another coefficient and that would be added. So like that it would go on. So this is the addition of the P0, P1, P2, P3 are the that products, x and m, x input and the coefficients. So if you look at this, assign y equal to a of 0, the initial here the value. So now with very interesting one we would like to introduce here, this is genvar, generate variable I. So this we have not used so far. This is the variable declaration again, which is very specific to the generate block. We can have the generate block, that is this is for the generate, can have generate and end generate, should have generate and end generate. Within this generate block we can use the variable that is local to this generate block is I. So this generate can be used for instantiating multiple things, multiple modules, or the case of generate with for loop, generate with if else statements can be used. Generate for I0, I less than L, I equal to I plus 1, begin, that is this is named multi generate. So you can see this P, the product is assigned Y within the generate for loop, pi equal to x into ci. So x is multiplied with the coefficients and stored in pi, and that p is taken over here, the products, all these are products, and then the added values are, the adder arrays are added to it. Assign and end, then end generate. So generate ends over here, and it is, this I is purely local to this generate. Okay. So generate and end generate is the new thing we are introducing in this code. And then assign y out, what is the y here, the adder array output to be the, so between y3 w3 minus w4 by w3 minus 1, that is 8 to 18 bits, the last the bits which are here of y is corresponding to the output. You can take out the output from it. Actually this is n module. So what we have done here in this case, that xn, this is the structure I was talking about. So xn is multiplied by h of 0, xn is multiplied by x1, h1 and h2, h3. So these products, okay, so x and these products are found from the generate block, that is generate and end generate, and that product, the delay, and this is the, these are the adders used here, this adder, and this addition is stored in the adder array, and then y out is taken out from the adder array, that is the last one. So then the last adder value will be taken out as y. So this sum of products and these coefficients are initially during the initialization of first always block, these are stored in the array, h of 0, h1, h2, h3, and then you get the products of them whenever x is appearing. X is one sample at a time, and the shift and add operation is given in the another always block. So for this, the test bench input, reset, load x and x in and c in outputs, output is that 11-bit output. Instantiate the module here with all of them clock reset, the same module x in, c in and y out. This is as usual we do in for the other modules as well. Initialize the inputs x in coefficient 0, load x equal to 1 initially, and then reset 0, clock 0, end it in initial begin. So display them and the monitor x in, c in and y out. So what is the signal we are going to give? Reset 0, first load x 0, so input c in is 124, and then c in is 214. After some time still this x is 0, you are loading it, not equal to times coefficients are loaded. This is 1 2 3. This coefficient can be again decimal 33. So this can be given. After that load x equal to 1, then make the coefficient 0. That means don't load the coefficients afterwards. So only the c in is this, all the 4 coefficients are stored over there. After this x in equal to 100, which is given, that is again to after the make 0, that is to have the impulse response of this 100, clock equal to not clock n module. So this is the test bench which gives us storing the coefficients. Okay, so here, whereas in the previous case we have this coefficients already in the written over in the Verilog module itself, whereas here we give these coefficients as inputs in the test bench. So making this we get, so for some time this 100, for the clock it is made 100 over here and then made 0. So the outputs we can see here. Okay, so 0, 48, 83, 22 and so on. So these are the loading of coefficients during this period. Reset is 1 here, so 0. After this made output will appear only after the input is allowed, and then the next clock edge you can see the outputs, and reset is made here 0 and load x 1, and this during this time load x was 0 and then load x is 1. So this output, which is the response of the filter, and you can also see the same thing over here in the console as well. So the realization synthesis process results in the technology schematic. Here we have the C-Reg, all the coefficients are given, and these are adders having the registers 1, 2 and 3 here, and then this is 4 adders here. Then the x input and the realization, which is just simply the diagram of the, you can see all of the inputs, load x, reset, clock and c input. X in is over here and you'll get the output y. So this is the technology schematic after synthesis. So this can be used in the realization, but the test bench should be replaced with in the real-time implementation, it should be replaced with the input real-time inputs, how we are going to give this 100 to the filter. Okay, so that the input 1 or 0 can be given and test the output. The output is a number of bits, 88 bits or 9 bits should be difficult to see in the board. You need for each bit you need to have the LEDs, or if you want to test each bit. But if you have this ADC and DACs that can be interfaced with the board through ADC, we can give an impulse input or the signal to be filtered, and then through DAC the output of the filter can be taken out and seen in the oscilloscope. So if you take the model which we had developed already, the FIR filter module. So this is the module. System input clock is this, reset the similar way what we have defined in the previous examples as well, x and y. These are the input and output declarations, reset and clock. The scale coefficients are, if you remember, 0.022 and minus 0.1037 and all those coefficients we have got, and we scaled up that to 10,000. So and store it here 222 the first coefficient, and then this next one, and these are the coefficients 225, 317, all the coefficients over here, storing them 0 to 8. Okay, so here these are the coefficients are stored in the program itself, and then always at passage of the clock or passage of the reset. If reset, then make the for loop and make all the taps. This is in the fashion of the first example which I had given. Tap I less than or equal to 0, y make y 0, After that, else begin. So give the shift, doing the shift with taps for I8 greater than 0, I minus 1, the tap shifting I less than or equal to I minus 1. Do that operation and give the assign this x to tap 0. So every clock edge that would shift. The filter output is the coefficient the tap 0, coefficient 1 into tap 1, and so on. So the assigned coefficient is multiplied with the tap 0, which is the input, and shifted input, shifted input, shifted here, tap 3 is shifted. So these shifts and coefficient multiplied here is this, and then given equal to. So output y, so n module. So this is the generating the y. Okay, so test bench for this inputs and giving the clock and everything, output y. Instantiate the module, clock reset input and output, and wait for clock. Always a clock of 10 nanoseconds, or the depends on the need, the clock can time delay can be, that is time period. Only thing is I would like to give you here is the task, a task operation here. The task wait cycles input integer n. So these are reusable codes, so task can be used to perform the same thing again and again. So suppose you want to use this here, let us see how we have used this reusable code. Integer I begin. So for I is for loop I less than n, I equal to n. So n is the integer for which, so how many cycles here it is used, the clock cycle, how many clock cycle an operation should wait for I at the passage of the clock. So this n is supposed to 2, so this would be at 2 passage of the clocks it would wait. This is an event control, if you recall, end and the end task. This end task is used for in the test bench. Let's see that how this is for waiting of the end clock cycles. Initial begin, and then display this $1. This is VCD file which is dumping the variables, and whatever this in the test bench, it would, all the variables will be the file created and dumping them. Initialize this first reset equal to 1, and how much time this reset should be 1. Okay, wait for 2 clock cycles. This is through the task 2 clock cycles, and then reset, make it 0. So again for the impulse response test, so we have the display, give this impulse input for the single impulse, how long the impulse should be. So we have manually reset that in the previous case somewhere, some point of time, the impulse input. Here you can wait for 1 clock cycle. Okay, so 1 wait cycle, this is through the task, and then it resets 0. So x equal to 0 here. Similarly for wait cycles 20, okay, so 20 clock cycle, after that this is for the 0 for 20 clock cycles. Okay, so 1 for 1 clock cycle, and then rest of the clock cycle, 20 clock cycle, it is 0. So this is the impulse input we can use through the task operation. And the step response, similarly we have this constant input 1, and how long, the way it should be 1 step response, the input step should be 1 for 20 clock cycles, whereas in the case of impulse input we make it for 1 clock cycle and then 0 for rest of the clock cycle in the impulse. So stop this operation and output, monitor this always at passage of the clock, give this details of the x input and module. So we have used this code. So you can see this 1 impulse input, the reset is also used with the task of 1 clock cycle, and then it is here, over here there is 1, and the output you can see the coefficients appearing here, the impulse input, the impulse response is nothing but the impulse coefficient itself. Okay, 22 to 2, so on. So you can see the impulse response, which are the coefficients we have loaded. So these are scaled coefficients for this particular operation. And the step response, you can see this one, this is appearing 1 for more than, after 1 initial this 20 clock cycles. So the step response approaching to, so if you scale it, it should be 0.9057. There's a small steady state error due to the approximations. Otherwise this works for the step response is shown over here. So with this we have we have done the Verilog codes of the 3. One is using the coefficients stored for the transpose structure. That same thing can be done for the FIR filter direct form 1 also. And then we have also learned the step response and impulse response, how to use the test bench, how to use the task for wait cycles of this giving reset and inputs and input when, and also how to use the shifting tap, using the tap uh, arithmetic shifts, how it helps in storing the codes, or storing these filter coefficients. Especially, what is the difference between arithmetic shift and the normal shift? We had the NAND shift operator, which arithmetic shift, how it helps in having the coefficients or using the coefficients in the Verilog module. So this is about the Verilog codes for FIR filter. We have learned the FIR filter design and the corresponding codes, how to develop this different styles. Window, especially I have covered window based method in the FIR, which is the popular method to use this design this FIR filter. We'll move on to the IIR filter for in the next lecture. Thank you.